because it's a little bit different from the way that the Manus Herbnet Ornis guidelines describe how to do things. The results are the same, the methods are the same, the uncertainties are calculated in the same way, but the real-world descriptions can be complicated. We saw that in the written descriptions in the describe this exercise, where to be specific, people write more than one description at the same time for the same place. BioGeomancer has to be able to understand that and not require you to use the calculator each time for each part. Okay? So first, I'll try to understand how to do this. This is all new to me. First, I want to show you, I don't know, the BioGeomancer web page. This is the project web page that was constructed while BioGeomancer was actively funded. At this moment, the funding for BioGeomancer itself from the Gordon and Betty Moore Foundation is finished, but development continues at UC Berkeley under the funding of the Ornis project. And in fact, there was a GBIF seed grant given to a group of people to further develop BioGeomancer web services, and in fact to try to georeference automatically all of the records in GBIF. That project hasn't really begun yet, but it's interesting to note that it's continuing in development. So this is the web page for BioGeomancer. It explains something about the history. It has links to georeferencing resources, etc. From here, there is a link that's quite hidden about how to go to the BioGeomancer. We're not going to go there right now. What I really would like to do is to switch over to the presentation to show you something about how BioGeomancer works. If you remember the first day when I talked about an overview of georeferencing, we came to the conclusion that it would require us 15,500 years to georeference the known occurrence data in the world, which we decided was a little too long. And we proposed that the partial solution to that problem is to try to automate georeferencing as much as possible. So my purpose today is to try to convince you that some of it is possible and some of it is not, and to give you an idea of where the problems lie in automation, and to show you this tool to describe how it's done. Another thing I'd like to point out is that BioGeomancer was a very large collaboration, and these are just a few of the people, basically the leaders from each institution who are involved in the production of BioGeomancer 3 years ago. So, what we have is spatially challenged occurrence data, descriptions in text in the native language, and they look something like this. But what we want is to be able to map those occurrence data. We've seen that all this week. We know that's why we're here. BioGeomancer, this is kind of a roadmap to the parts of BioGeomancer and what it does. And what I'm highlighting in blue here is the center part, and the part that I talked about right now. It's the part that actually takes the textual description and tears it apart, tries to understand it, then applies the georeferencing rules to come up with a point radius in the end. So there's several different parts of it. There's a locality interpretation part, there's a spatial description part, and there's an uncertainty calculation part. Here I want to point out that part of the BioGeomancer project was to further develop geolocate and to try to bring it in line with the best practices in georeferencing. And also, I think that some of the work they've done to internationalize it has come from the BioGeomancer project. As well, the part of the project was to make it possible for BioGeomancer's workbench to call a geolocate web service so that it can use the geolocate data and the geolocate algorithms to do georeferences if this part of BioGeomancer was incapable of doing so. Okay, so now I'll start to talk about the process. How does BioGeomancer understand text? So, as I've said before, what we have are the verbatim locality strings. I say verbatim because it is possible to put in your text without trying to clean it up. We'll see how well that works in a little bit, but that's the point that I want to make, is that we try to reduce the amount of work as much as possible. So what we'll do is try to introduce the text without cleaning. So again, here are my examples of textual descriptions. So we have some issues about locality descriptions that come from the past. One, we must try to treat that locality description as accurate. By that, I mean the collector actually wrote down where they were. They're not lying to us, right? We have to accept that what they wrote is what they meant and is where they were. We have no alternative. But we have to be aware of that. Second, we need to treat those locality descriptions as complete. That is, they told us everything. We can't assume things they didn't tell us. Okay? That is to say, these we must assume in order to begin. If we can't assume these, then we might as well not try to do a reference. But they aren't necessarily true. Okay? So, as a first step, we accept this. As a second step, we test it. So, the next thing is to try to apply rules to interpret those textual localities. That's one thing that I think we haven't really tried to do in georeferencing so far, because we're humans and we have brains. We're the ones who write those descriptions to begin with, and so it's easy and almost transparent for us to understand what's written. We don't go through some algorithm, at least not in the forefront of our mind, about how to interpret those localities. Some difficult ones, it seems like we have to go through an algorithm, but the easy ones is natural to understand what they mean without really being very specific. So now I'm talking about this part of BioGeomancer. One thing to be aware of, we've seen this in our exercise, is that there's more than one way to make an interpretation. Okay, how do we do it? We do it two different ways in BioGeomancer. One is to apply regular expression analysis. This is a method that's used by geolocate, and I think that David had described how first the geolocate will look for the distance. It'll look for a number followed by units and take that out and say, okay, I know this part. Now, I expect there to be some named place following that, or some direction following that. That's basically applying regular expressions, one after another, to try and figure out what the locality means. This is also the method that was used in the very first BioGeomancer. I call it BioGeomancer Classic, which is still online. It's a very simple version of a single georeference that has no uncertainties or anything like that. So we incorporated these regular expression methods, but also we did some experimentation and some research in machine learning and natural language. Whereas regular expression analysis is applying a specific algorithm, one after another, test for distance, test for units, test for direction, test for a named place, etc. Machine learning is a statistical process. In machine learning, what you do is you find a whole bunch of localities of all different types, and you mark it up. And you say, this part of the locality means this part means this, etc. And you create a very large data set of examples. And then you apply those examples to a machine learning algorithm. And so when the new locality comes in, it tries to match the locality to a pre-existing pattern that it sees statistically. And it says, for example, the chance that this is an offset at a heading from a named place is 58%. And that's the best match that I have with any other locality type. It will try to apply that locality type and interpret it. This type of processing, salud. This type of processing was, and research was done at the University of Illinois in Urbana-Champaign, and we also experimented with some pre-existing software from Insight Software Incorporated. So we tried lots of different ways to do this, with interesting results, by the way. I won't talk about the results right now. What I want to talk about is the process now of interpretation. So we've seen in our experimentation, in our exercises, that there are many different locality types. If we try to make a category, there are many different kinds. And you've seen these locality types in the georeferencing calculator, in the calculation type. Sorry. First we do a calculation type, then we do a locality type. Basically, these are examples from the list on the georeferencing calculator of locality types. One is a simple feature, like Madrid. Another is a path, like a river or a road. We distinguish between these two because the geometries are different. There is an offset from a feature without a heading. This is 5 miles from Madrid, without saying what direction. This one is the same thing, but with a direction, 5 miles north of Madrid. This is the orthogonal offsets that we've seen already. And then we start to get into some very strange locality types. And there are many of them. They're not just the 6 or so that we find in the georeferencing calculator. There's actually quite a bit of creativity in the world about how to write localities. We saw that in our own exercises. The interesting thing is that from an analysis of 500 random records from the MANUS project, the prevalence of different locality types turned out to be like this. So it's very common to have a feature-only locality type in a description. It's also very common that a locality is never recorded at all. It says no specific locality recorded or unknown, something like that. But it's saying specifically we don't know where it came from. After that, the feature offset heading is the most popular, followed by simple paths, followed by things that are unknowable, even by humans, unless they were the collector. Something like this. That's a real example. I don't know what that means. BioGeomancer doesn't know what that means either. Okay. So now I need to introduce a concept that BioGeomancer uses to continue. And it's the concept of a clause, or in Spanish, un cláusula. So it's a part of the locality description. Sometimes it's the whole locality description, but sometimes it's only part of it. And it's a part of that locality description to which we can apply a locality type, one of those 36 or so, rather than making it some complex combination. So if I take this as my data set and try to apply the clause boundaries to it, being my first step, I take this as a locality description and I put boundaries around it and say this whole thing is the clause. I can't really reduce that. I could take that part out and say that's a feature only, but then this part doesn't make any sense. So the whole thing together makes sense, and it's a feature offset heading. Feature offset heading. Now, this could be in lots of different forms. It might say 5.5 kilometers north of La Piñeta. Or it could say 5,5 kilómetros al norte de La Piñeta, or whatever. Lots of different forms. Here's another one, where the whole description contained both of these things, but when we apply clause boundaries, we find out that we have one clause here, a feature only, these mountains, and one clause here, a path only. Sorry, it's a separate type that wasn't on the list. It's a subset or subdivision of a path. It's only a part of it. Okay, so two clauses in that case. And we can do the same thing for all of those examples. Here's another simple one, feature only. Here's one that has a feature offset heading as one clause and a path. Here's a near a feature locality type. And here's an orthogonal offsets from a feature locality type. So each of these last two has just one clause. Even though in terms of language we have a clause separator, right? So it's quite complicated actually. If we were just to take our clause separators and say that's one clause, that's another, in two cases here, which are quite common, we would have destroyed our ability to understand the locality. So we have to be a little bit smarter about how that works. So the second step is to determine what that locality type is. First we knew that that was a clause. We did so by a pattern or by statistics, and then we applied the type to it. So all I've done here is to say, yes, this is my clause inside, and the type is feature offset heading. This is just notation for our purposes now. This is a feature only. This is a abbreviation for a subset of a path, etc. Feature only, feature offset heading, path only, near a feature, and orthogonal offsets from a feature. Okay. Second step is to define what that type is. The third step is actually to figure out the parts inside each clause. So in this clause, La Piñeta, I know it's a feature offset heading, which means I need to have a feature, I need to have an offset, I need to have units for the offset, and I need to have a heading. So my next step in interpretation is to pull out of there all the parts. Basically, I'm filling in the calculator at this step inside of BioGeomancer. There's a feature description. Let me go back. How do I go back with this? No, say? Like that. Okay. What I wanted to point out here is now, these are all the attributes that we need. But if you remember in the calculator, the next step is to find the coordinates of La Piñeta. It would be quite sad in terms of automation if we had to stop in BioGeomancer now and go to Google Earth or to the NEMA database or to Diva GIS or something else to find out where La Piñeta is. So the next step is to find out where La Piñeta is, and that comes here in the spatial description part of BioGeomancer. So what we have to do is look up La Piñeta in a gazetteer. In a gazetteer, there should be an entry for La Piñeta. If there isn't, we actually can't proceed. So no georef because can't find La Piñeta. But if we can, then we have to make a new assumption, this is a data issue, that the reference that we're using in the gazetteer is accurate. Right? Another assumption we shouldn't hold to be true. As we've seen from NEMA data, because it's only to the nearest minute, oftentimes the point is away from the town or whatever. Also, especially for a river, there's a point in a gazetteer, but the river is quite long, and the point is at the mouth of the river, the end of it. So it's not a very good description, but it does help us find the place. So for a moment, we'll say we'll use it to find it on a map, but we reserve the right to change it in the future if it doesn't match our understanding or knowledge of reality. Okay? We're always hypothesizing and then testing. Okay, so back to the example of Davis in Yolo County, California. How does BioGeomancer try to understand this? It tries to make a shape. If possible, that's what we would like to have as our end result. So we want to apply rules to build that spatial description. Here's an example of a rule. There will not be a test on this, but it's meant to demonstrate to you that rules, though perhaps aesthetically pleasing, can be complex. This is the example. Go one more to see if I have it. Yeah. This is an example of different ways that one might try to calculate what it means to be west of some place called B. It's a very difficult kind of description because we don't really know where to stop when we go west. I'm not going to describe which of these we use or anything like that. It's just to demonstrate that our problem now is to try to get a shape. Okay, so our sixth step is to construct a final spatial interpretation. We have shapes from a gazetteer. We have shapes from each clause from a gazetteer. So, in this example, we have the two clauses, 10 miles southwest of Cañas and Rio Higueron, which we assume to be a feature offset heading in one and a path in the other. So, in order to get a final georeference, what we have to do is we have to assume that both of these are true at the same time. Simple enough. How do we do that? In geometry, the place where both of those are true at the same time is where they intersect. Right? Each one has a shape. We take the intersection of those two shapes. That's where everything is true. That's our final georeference. Now, I noticed in the describe this exercise that that's how the humans thought as well. If there was a complicated description that had two clauses like this, what you would do is interpret one of them and find out where that was. Then you'd interpret the other one and find out where that was, and figure out the point that was in the middle of both of those. BioGeomancer is doing the same thing. Finally, what we want to do is to apply criteria to reject hypotheses that don't make sense or that have lower value in order to reduce the numbers. Ideally, in the end, we want one. We want a single best georeference. Doesn't do us much good to share the 15 possible versions of where Rio Higueron might be. That's a case where in the georeferencing for dummies or the best practices guide, we would say no georeference because too many possibilities. Okay? Okay. So finally, what we'd like to be able to do is to be able to apply user preferences to how some of these things are determined or how to prioritize the possibilities. So one example might be to distinguish between marine and terrestrial locations, because our perspective is quite different based on the two of those. Let me give you a quick example. Suppose this is a coastline, and this is a bay. This is land. This is sea. And this bay has some name. My bay. And the description in our database says, my bay. Where's the georeference? Kind of depends on what kind of critter it was or what kind of plant it was. If it was a marine specimen, then my bay should probably be out here somewhere. But if it's a terrestrial specimen, it should be on land somewhere. And we have rules about how to figure out where it should be on land versus where it should be on sea. So the idea is that we should allow users to say, I want to assume that it's on land, and apply the right rule to get the georeference to fall on the land. Similarly, we might have other categories of preference. Another big one, and I hear mumblings from the HerpNet crowd, is we want to be able to assume that the offsets follow roads as opposed to going in a straight line. Those are very different georeferences, and they might be done in very different ways. Quick example there is, here's my starting town, center of the starting town, and I have a road. It goes like that. And my description says 5 kilometers east of this town. If I go directly east, I end up here, by air. By air. If I follow the road, I end up right here, by a road. Because those are very different, I should have different methods to calculate them, and I should give the user the preference to decide to use one versus the other. If I'm a herpetologist, I want to use by road, for example. Okay? So, in the output, what we want is to keep the original data for comparison. We want to know what the input was. We want 0, 1, or more spatial interpretations to come out of it, based on however many it can determine. Ideally, with a spatial footprint. We want a shape to come out, if we can. We want a point radius version of the shape in case the end user can't use this one, or even because this is useful all on its own for filtering. Because you could say, from the point radius part of it, give me descriptions that have a size less than 1 kilometer, and then use the shapes of those. So both of them are useful at the same time. And ideally, we should have in there the information about what BioGeomancer did, what the preferences were that were applied, what omissions there were. For example, BioGeomancer may not use all of the clauses because, for example, one of the clauses was this. But there was other information that BioGeomancer could determine. That shouldn't stop us from making a georeference. We just make a georeference that doesn't include this information. Okay? So if we do that, we should say what it was that we did not use. And finally, if possible, if it's reasonable to do so, we should try to give confidence values about georeferences that come out of BioGeomancer. In conclusion, then, it's important to understand that a georeference is a hypothesis. It's not a measurement. And as with all hypotheses, they require testing. And the ones that are tested, you should note that they've been tested because you've applied some work, and the work that you have applied is useful for others to know. This is where the georeference verification status comes in. If you take a georeference and then show it to the collector, and the collector says that's perfect, we should note that. It's been a tested hypothesis, and so it should have high data quality. It should be useful for people. We can't do any better than that. That's it for describing how BioGeomancer works. This slide shows that there were quite a lot of people involved, and it's the reason I have gray hair right here and right here now. Okay.